again we will come back, right. So, now from equation 56 and 58, right, we will get this equation 56 is this one 2 pi f upon beta, right, and equation 58 we have seen beta is equal to omega root over L C, right. So, therefore, V is equal to omega by beta actually, and it is beta is equal to omega root over L C. So, V is equal to 1 upon root over L C, right. Therefore, this is equation we have marked V is equal to 1 upon root over L C 60, equation 60, right. Now, lambda is equal to, we have seen beta lambda is equal to 2 pi. So, lambda is equal to 2 pi by beta, and it is 2 pi and beta is equal to omega root over L C. So, omega 2 pi f. So, it is 2 pi upon 2 pi f root over L C. So, 2 pi will be cancelled and lambda is equal to 1 upon f into root over L C. This is the wavelength. This is equation, this is the equation of the wavelength, and this is equation 61, right. Now, we will make some approximation. So, now for a single phase line, while we are conducting inductance and capacitance, we got L is equal to mu 0 by 2 pi L n d upon r dash, right. This we got, this we are for the inductance calculation we got this, right, and capacitance C is equal to 2 pi epsilon 0 L n d upon r, these two we got. Now, multiply these two L and C. If you multiply L C is equal to mu 0 epsilon 0 L n d upon r dash divided by L n d r d by r, right. Now, we will make an approximation that we will assume, we will approximating it that L n d upon r dash, the natural log d upon r dash is equal to L n d upon r. This is an approximation, we are making it an approximation, right. If it is so, if these two are equal approximately, if we show, then L C actually is equal to mu 0 into epsilon 0. This is equation 62, right. So, if substituting this expression of L C from equation 62, I mean this one, into equation 60 and 61, right. That means, if you substitute this equation in equation 60, that is V is equal to 1 upon root over L C, and in 61 while lambda is equal to 1 upon f root over L C, you substitute here, right, that your L C is equal to root over your what you call sorry mu L C is equal to mu 0 epsilon 0. If you do so, if you do so, then V will become 1 upon root over mu 0 epsilon 0 and lambda will become 1 upon f root over mu 0 epsilon 0, right. So, you know the mu 0 value 4 pi into 10 to the minus 7 Henry per meter, and you know the epsilon 0 also 8.854 into 10 to the minus your 12 farad per meter, right. So, approximately V will be 3 into 10 to the power 8 meter per second, which is approximately the velocity of light at frequency 60 hertz, right. So, this is that your velocity, and wavelength lambda will become 5000 kilometer. If you put in that second equation here, right, lambda will become 5000 kilometer, right. This is more or less some ideas regarding your velocity of propagation and your wavelength lambda, right. But this is approximate, these values are approximate, we have, because we have taken L n d upon r dash approximately is equal to L n d upon r, right. But this will give a good idea about this thing, about your V and your lambda, right. Now, for a lossless line, we have seen for a lossless line gamma is equal to velocity of propagation alpha plus j beta. So, alpha is 0. So, for a lossless line gamma is equal to j beta, right, and the hyperbolic function cos hyperbolic gamma x actually will become that if you substitute gamma is equal to j beta for a lossless line, it will be cos hyperbolic j beta x is equal to nothing but cos beta x, right, and sin hyperbolic gamma x is equal to sin hyperbolic j beta x is equal to j sin beta x, right. So, it is simply j sin beta x. So, if you take those expression and put this value, you definitely will get the cos hyperbolic j beta x is equal to cos beta x. Details are given while developing long transmission line, so not showing it here, understandable, right. The equations for the RMS voltage and current along the line is given by equation your 38 and 39, right. So, equation 38 actually this and 39, these two equations rewriting here, right. V x is equal to cos, in that case instead of cos hyperbolic x, we are putting cos beta x for a lossless line. Just now we have written here, cos hyperbolic x for a lossless, cos hyperbolic gamma x is equal to basically cos beta x, where alpha is equal to 0 and gamma is simply j beta, and cos hyperbolic j beta x is equal to cos beta x. So, instead of cos hyperbolic, we are writing cos beta x V r plus z c j z c, rather j z c sin beta x I r, because sin hyperbolic hyperbolic gamma x is equal to sin hyperbolic j beta x is equal to j sin beta x. Similarly, here also, right, this is all this, you just replace those hyperbolic term, you will get I x is equal, that is equation 38 and 39. In equation 38 you put that, equation 39 you put for I x, right. Then you will get j 1 upon z c sin beta x V r plus cos beta x I r. This is equation 66, this one 65 and this one 66, right. Now, at the sending end, because we are measuring the distance from the receiving end to sending end. So, at the sending end x is equal to L. So, V x equal to V L is equal to sending end voltage V s, right. Similarly, I x is equal to I L is equal to I s, right, this one. So, sending end voltage can be written as cos beta L V r plus j z c sin beta L I r, this is 67, and I s is equal to j upon z c sin beta L V r plus cos beta L I r, right. So, actually for quick calculations of ABCD parameters, this equation is, I think, less laborious, I mean easier to compute, right. This equation 67, but 68, but remember this is for a lossless line, right. Now, that is why I have written for quick calculation, it is easier to use 67 and equation 67 and 68, right. Now, terminal conditions are readily obtained from equation 67 and 68, that means all these terminal conditions you can easily get it from equation 67 and 68, right. So, for example, for the open circuit line, that receiving end current is 0, I r 0 when line is open circuit, right. And from equation 67, right, that means from this equation 67, this equation you put I r is equal to 0 in equation 67, here you put, this is for open circuit, right. If you do so, the no load receiving end voltage will become, at that time at the line is open circuit. So, I mean condition, no load condition is that when line is open circuit, when I r is equal to 0, right, when I r is equal to 0 in this equation at no load, when I r is equal to 0, V r is equal to V r N L, right. So, when we are telling that when I r is equal to 0, right, here I am somewhere I am writing that V r is equal to V r no load N L, right. So, I am not writing here, but understandable that when open circuit line I r is equal to 0 and V r is equal to V r no load, that will be easier to understand. Therefore, this equation, that equation 67, it will become that V s is equal to cosine beta L and V r is equal to V r no load, because I r is 0. Therefore, V r N L is equal to V s by cosine beta L, right. So, that is what I am writing, V r N L is equal to V s upon cosine beta L, right. That is equation 69. So, what does it signify? That at no load condition, that receiving end voltage, right, is greater than the sending end voltage, because cosine is less than 1, right. This is sometimes, this is called Ferranti effect, and this is happening because of your charging admittance in the line, right. So, and no load condition, this is happening. So, that is why V r N L is equal to V s upon cos beta L. This is approximate, but in the same your long line expression also same logic you can use, and you will find that V r N L will be greater than the sending end voltage at no load, right. So, that is why at no load the line current is entirely due to the charging capacitive current, and the receiving end voltage is higher than the sending end voltage, because when line is no load, there is no, I say line, no line is there is no load connected here, right, but charging capacitance are there. So, because of that your what you call this that receive no load voltage is becoming higher than the sending end voltage. So, suppose a transmission line, this is a question to you. Suppose a transmission line is your this thing what you call not carrying any power under no load condition, right, and it is not carrying any power. Suppose a man standing on the ground with bare feet, say, with no proper protection or insulation, and taking a conducting rod and touching that conductor, what will happen to that person? I repeat this. Suppose a line transmission line, high tension transmission line was carrying power, but after that the load is disconnected. So, now this condition whatever you will putting that IR is 0, right, it is not, but a man standing on the ground, right, with bare feet, say, right, and taking a conducting rod and touch that conductor, that is the line, right, what will happen to that person? This is a question to you, right. Later you can send this, when you listening this you send your answer to me, right, but here I am not giving that answer, right. So, this one next, for a solid short circuit, right, for a solid short circuit at the receiving end, solid means there is no fault impedance, fault will come later, right, much later. So, for a solid short circuit at the receiving end, the VR is equal to 0, right, and in equation 67 and 68, that is your this equation 67 and 68, these two equation, you put that condition that for VR is equal to 0, right. If you do so, then you will get sending end voltage is equal to JZC sin beta L IR, this is equation 70, and IS is equal to cos beta L IR, this is equation 71. The above equation actually can be used to find the short circuit current at both ends of the line, right. Next is that your surge impedance loading. When the line is loaded by being terminated with an impedance equal to its characteristic impedance, that is Z is equal to ZC is equal to root over L by C, right. The receiving end current you can define, that means when a line is loaded by being terminated, right, with an impedance equal to its characteristic impedance, the receiving end current will be, receiving end voltage is VR, and it is and that loaded and that line is loaded by being terminated with an impedance equal to your characteristic impedance, that is ZC. That means IR will be VR upon ZC. This is equation 70, because receiving end is VR, a line is terminated with an your what you call with an impedance equal to ZC. So, IR will become VR upon ZC. This is equation 72, right. Now, for a lossless line, ZC is purely resistive, because we have seen ZC is equal to root over L by C. So, the load corresponding the surge impedance at rated voltage is known as the surge impedance loading, that is SIL, right. So, this load, so for ZC is a purely the load corresponding to the surge impedance at rated voltage is known as surge impedance loading, they call SIL, and is given by SIL is equal to 3 VR IR conjugate. This we have seen also, I have shown you separately how this VR IR conjugate or VR conjugate IR it comes, right. So, this is 3 VR IR conjugate is equal to this IR is equal to VR upon ZC. So, this is actually 3 VR IR conjugate, right, and IR is equal to VR upon ZC. So, it is VR and your VR upon ZC conjugate, right, multiplied by 3. This is 3 VR conjugate and ZC, because ZC is a real quantity. So, VR into VR conjugate, it is 3 VR square divided by ZC, right. So, that is why we are writing that this one is equal to SIL is equal to 3 into voltage magnitude VR square upon ZC. This is equation your what you call this thing, and VR is your phase voltage, that is why this is multiplied by 3, right. So, since VR is equal to VL rated upon root 3, that is V line rated voltage we are taking here in general. So, SIL in megawatt, it becomes SIL is equal to KVL KVL rated whole square upon ZC megawatt. What we are doing is VR is equal to VL rated upon root 3 we know, but this rated voltage we are actually making it to kilovolt, that is why I am writing KVL rated. Then suppose it is suppose KVL rated means suppose 220, the 220 square upon ZC, what will be there, this is kilovolt, right, this is kilovolt, and that is square and this ZC is the ohmic value ohm. So, this is actually megawatt, right, because it is kilovolt square, and this is actually equation 74, right. Now, substituting this is IR is equal to VR upon ZC, that I told you, right, in equation 65. So, in equation, this is actually equation 65 I have rewritten here, right. So, cosine beta x VR plus ZC sin beta x IR. Now, this IR is equal to VR upon ZC, you substitute here IR is equal to VR upon ZC, then ZC will be cancelled. I have substituted here that this is VR upon ZC. So, ZC will be cancelled, and it will become actually cosine beta x plus J sin beta x into VR. That means, Vx is equal to VR angle beta x, this is equation 75. Similarly, that your equation, your what you call that in equation, see this VR, same thing here, writing it other way, that VR upon ZC is equal to IR, you substitute it in equation 66. So, equation 66 I am writing here that Ix is equal to 1 upon ZC sin beta x VR plus cos beta x IR, right. So, VR upon ZC is equal to IR, you substitute. If you do so, that skipping this line, same thing, just rearranging, Ix is equal to cosine beta x plus J sin beta x into IR. That means, Ix is equal to IR beta x, right. That means, this equation 76 Vx is equal to VR angle beta x, and here in 76 Ix is equal to IR angle beta x, then whatever may be the value of x, right, that VR and IR at every point of x, that Vx and VR, that value remains same, right. That whatever may be the value at any point of x, Vx is equal to VR, VR is totally independent of x, and here also IR totally independent of x. So, Ix is equal to this IR and VR will not change, even x is changed, right. At every point this Vx and Ix both remain same, right. That means, it shows that in a lossless line under such impedance loading, the voltage and current at any point along the line are constant in magnitude and are equal to their sending end values. If you put here x is equal to L, that means Vx means Vl is equal to this will be then Vs is equal to VR angle beta L, and this will become Ix is equal to rather Is is equal to IR angle beta L, right. That means, and in magnitude and are equal to their sending end values, right. Since Zc, so any point you take, right. So, the Zc has no reactive component, we have seen that Zc is equal to root over L by C. So, there is no reactive component, that means, in the line Qs is equal to Qr is equal to 0, right, under this condition, right. So, this indicates for surge impedance loading, the reactive losses in the your line inductance are exactly offset by the reactive power supplied by the shunt capacitance, right, that is your charging capacitance, right. So, if it is true, then your omega L IR square will become omega C your VR square, right, if this is true, right. So, then your if you use this condition, right. So, you will get Zc is equal to VR upon IR, if these two are equal, then it will be root over L by C. That means, that your what I will say, right, whatever your this thing that this inductance, the line inductance is exactly offset by the power supplied by the shunt cap. That means, your this one, that the line inductance is XL is equal to L omega, right. So, that is right. That means, your what you call IR square into your IR square XL is equal to L omega IR square. So, that way we are writing actually omega L IR square, right, and the charging admittance is omega C VR square, right. So, in that case, that power supplied or this reactive power supplied by the charging admittance, actually it is your VR square by XC, right, and you know XC is equal to 1 upon omega C. So, you substitute here, you will become omega C VR square. So, that is why this total your reactive losses supplied by the your charging capacitance. So, that is why omega L I square is equal to omega C V r square, from which you will get it that Z c is equal to V r upon I r is equal to root over L by C, which verifies the result in equation 59, right. So, that means when you have your this thing this kind of condition that there is no reactive power in the line, right. Then what does it mean for surge impedance loading? So, that means for surge impedance, first you see for surge impedance loading for a typical transmission line varies approximately from 150 megawatt for 220 kV line, these approximate values, to about 2000 megawatt for 765 kilovolt lines. But generally this line actually when it is operated as full load or this that, it operates much above the surge impedance loading. So, SIL is a useful measure of transmission line capacity, as it indicates a loading where the line's reactive requirements are small, right. For loads significantly above SIL, shunt capacitor may be needed to minimize the voltage drop along the line, right. Generally line operates above this limit, right. While for light load significantly below SIL, you need basically shunt inductors, right. So, if it is above the surge impedance loading, then you need shunt capacitor, and if it is below the surge impedance shunt impedance loading, then you need shunt inductor, right. So, generally the transmission line full load is much higher than the surge your what you call that surge impedance loading. So, whatever this thing we have studied for this long transmission line, that one is that surge impedance loading, then we have studied velocity of propagation, then that wavelength lambda, right, and that physical significance of the your surge impedance loading and the terminal conditions, and then we saw that under no load condition that charging this thing your what you call receiving end voltage is higher than the sending end voltage. This is a typical phenomena for a transmission line, right. This is how this happens due to your charging admittance, right. So, these are the things we have studied, but we will take a small example of this your what you call velocity of propagation, then surge impedance. After that we will go to for 3 phase your what you call power flow through transmission line, right. And so, this one we take a small example, right, that a 3 phase 50 hertz 400 kV transmission line is 300 kilometer long. The line inductance is 0.97 millihenry per kilometer, right, per phase, and capacitance is 0.0115 microfarad per kilometer per phase. So, assume you assume a lossless line, you have to compute beta as the line beta, that is the line phase constant Z c, the characteristic impedance or surge impedance, V velocity of propagation, and lambda the wavelength, right. So, this thing solution is very simple, you know beta is equal to omega root over L c, it is 50 hertz system, L is given, C is given, all you substitute, you will get beta is equal to 0.00105 radian per kilometer, right. And then surge impedance is Z c root over L by C, L is given, C is given. So, it is 290.43 ohm, right, and velocity of propagation V is equal to 1 upon root over L c. So, L is known, C is known, you substitute, you will get 2.994 into 10 to the 5 kilometer per second, right, and line wavelength lambda is equal to V upon F, right. So, is equal to 2.994, we have seen no lambda is equal to your F 1 upon your what you call F root over 1 upon L c, that is basically V upon F. So, because V is computed here, so you put the value of V divided by F. So, approximately 4990 kilometer, right. This is your the small example for this one, but after this we will go for power flow through transmission line, right. So, in terms of your A, B, C, D parameter. So, this one I will get it for you for the receiving end one, and sending one I will give you the your final expression, but you can derive this, right. So, you consider a sample power system as shown in figure this. So, this side is sending end side. So, power is taken P s plus J Q s, this side is receiving end side, So, power is P r plus j q r, this is load. Sending end voltage is magnitude V s angle delta s, receiving end V r angle 0 degree. So, it is actually your taken as a reference, right, and this line is represented by A B C D parameter, that is why I am writing here A B C D, right. And so, we assume now first let A is equal to magnitude A angle delta A, B is equal to magnitude B angle delta B, all this thing, D is equal to A is equal to magnitude A angle delta A, because throughout that we will replace by this thing, instead of D we will write A, because A is equal to D, right. V s is equal to write magnitude V s angle delta S, we have made it here. V r is equal to magnitude V r angle 0, we have made it here. So, from equation 1, that is very fast equation, right, for this topic. We have V s is equal to A V r plus B I r. So, from here it is coming I r is equal to V s minus A V r upon B, right. So, V s, V r, A, B all you substitute in terms of their magnitude and angle, right. Therefore, angle V a, this one, right, magnitude V s angle delta s. So, minus mod A angle delta minus mod V r angle 0 divided by mod B angle delta B, right. Now, so in that case, so this one you all these things you simplify, this equation you simplify, then you will get I r is equal to mod V s upon mod B, it will be angle delta s minus delta B minus mod A mod V r by mod B angle delta A minus delta B. This is equation 77. We are also same thing we have seen, the receiving end complex power S r, it is receiving end power 3 phase, that is why writing 3 phase is equal to P r 3 phase plus j q r 3 phase is equal to 3 into V r I r conjugate, right. This is equation 78. Now, from equation 78 and 77, if this I r is given, so you have to find out what is I r conjugate, right. So, if you take the conjugate, this is I r, if you take the conjugate one, so V s upon V will remain, and as it is conjugate, so this angle will become delta B minus delta S, right. That is why in this expression it is delta B minus delta S, and for this conjugate this angle also will be delta B minus delta A because of conjugate. So, this angle is delta B minus delta A. So, it is 3 into mod V s upon V r upon mod B angle delta B minus delta S minus 3 into mod A mod V r square upon mod B angle delta B minus delta A, right. So, in terms of the your what you call this line to line voltage, right, if you take this line to line voltage, then we can write this expression, it is 3 V s V r, that means it is 3 V s V r, right. This one you can write, no, it is root 3 into V s into root 3 into V r, right. So, this one actually will become, I have taken here, it is V s line to line, right, into V r line to line. So, this term is taken, that V s magnitude V s line to line, V r line to line by mod B angle delta B by delta B minus delta S, right. So, these 3 actually written like this, and similarly this A V r square, right. So, in that case also this can be written as actually root 3 V r your square, because these 3 I take it inside that bracket. So, root 3 V r square. So, basically this one can be written as V r line to line your square, that is why it is written V r line to line square upon mod B angle delta B minus delta A, right. We will come back soon. Thank you.